Good morning, Applied Physics students. This is Mrs. Kremschreider with some notes for you to add to your tag or possibly to just have in your notebook and you're taking some notes. I think these notes, the purpose of taking the notes is that hopefully when it comes time to take a quiz or a test over this unit, you'll have most of the information in one spot, which should make it a little bit easier to use your notes and such for your open book and open note quizzes and tests. So we are talking about chapter 3, which is titled Newton's First Law of Motion. Oops, 3. Which is also called inertia. So obviously this title is, or this chapter is about Newton's first law of motion. And your textbook kind of starts a little bit with some history. The big idea in this chapter is that we're going to see that forces cause changes in motion, which we already kind of saw a little bit in chapter 2, but we're going to kind of elaborate upon this, okay, and expand this. So first, your textbook talks a little bit about Aristotle, and I'll just do some brief notes. I'm not a big history buff and that into history, but Aristotle was an ancient Greek, and he studied motion and divided it into two types. One of the type was natural motion, and he thought that the natural motion was straight up and straight down. So basically he was probably dealing with gravity, but he didn't call it gravity at the time. Okay, and then he said that the other type was violent motion, which maybe isn't violent in the way that we think of it, but he just said that this violent motion was the result of some sort of force, some sort of push or some pull on an object. Okay, so he was kind of the first scientist. Your textbook also talks about Copernicus. And Copernicus reasoned that the simplest way to interpret astronomical observations So Copernicus is this next scientist that your textbook talks about, and he reasoned that the simplest way to interpret the astronomical, which just means kind of like observations about the sun and the moon and the planets, was to assume that Earth and the other planets move around the sun. So again, this is kind of contradictory to what was believed at the time. At the time, everyone believed that the earth was the center of the universe and everything moved around the earth. So Copernicus is kind of telling everyone that they're wrong and saying, no, the sun is in the middle and all the earth and all these other planets move around the sun. Again, because of that, his beliefs were controversial, which just basically means that people didn't believe them at the time. Again, right, in hindsight, everybody now knows that the sun is the center of our universe and that the planets do go around it. But at the time that Copernicus said this, it really wasn't accepted by the people of the day. The next scientist that your textbook spends a little bit of time talking about is Galileo. And just remember that we've already talked about what a force is and that it's any push or pull. Galileo kind of understands a little bit more about friction. And friction is the name given to the force that acts between materials that touch as they move past each other. Okay, so that's kind of our science definition of what it means or what friction is. Friction really is caused by irregularities in surfaces. Oops. Which basically is just talking about bumps. So what we're kind of saying here is the bumpier a surface is, or two surfaces are that are in contact, the more friction there will be. The less bumpy the surfaces that are in contact are, the less friction. And an example of this really would be thinking about your automobile tires, right? Good, fresh, brand new automobile tires have really big bumps on them, right? And they have those channels. And poor tires that have been worn, they're kind of flat. They don't have very much bumpiness left, right? And so poor tires can lead to accidents because there's not as much friction between the tire and the road, and you're more likely to slide or come off of the road or lose contact with the road. Okay, so friction is this force that acts between materials when they touch as they move past each other. It's caused by these irregularities in the surfaces or the bumps or bumpiness of a surface. And Galileo said, only when friction is present is a force needed to keep an object moving. So kind of another way to say that is Galileo is saying if there's not friction, like in outer space, if I threw a ball in outer space, there would be no force required to keep that ball moving. Okay? And so basically he's saying here on Earth, where we can't escape friction because we can't escape gravity, we have to have some sort of force to keep an object moving. So this is always true on Earth because of gravity. So on Earth we have gravity, okay, which causes friction between anything. Like if we roll a ball on the ground, even if it's a really smooth ball, there's still friction that occurs there because of gravity, and eventually that ball would stop moving. Okay, so again, Galileo's kind of explaining some things about Earth. So another way that kind of Galileo describes friction is Galileo says that friction is the tendency of a moving object or body to keep moving is natural. And remember, that's kind of contradictory to what Aristotle thought. Aristotle said natural means you're not moving, okay? And every material object resists a change to its state of matter. Sorry, not state of matter. State of motion. So again, he has this idea that it's because of friction that objects don't keep moving on Earth. And he says actually an object would keep moving. That's kind of natural once we give it a force. Okay? And that if an object's moving, it's going to want to keep moving. And if an object is at rest, it wants to stay at rest. Okay? So again, Galileo has talked about what's known as inertia. And inertia is a property of a body or an object to resist changes to its state of motion. So there was a page 32 think question. The page 32 think question says, a ball is rolled across a countertop and rolls slowly to a stop. How would Aristotle interpret this behavior? Right? Aristotle, he's the one who says that that ball stops because its natural motion is to be at rest. How would Galileo interpret it? Okay, so Galileo is going to say that that object stops because friction resists it or hinders it. And the last question, how would you interpret it? Well, that's up to you. The next section talks about a scientist that hopefully you've heard of before, Isaac Newton. So Newton's law of inertia. And this is really Newton's first law. He has three. We're going to learn about all three. And this is his first law. Newton's first law is also known as the law of inertia. So the law of inertia, Newton's first law, it's two different names for the same thing. And Newton's first law states that every object continues in a state of rest. So basically what he's saying is if an object is not moving, it's going to stay not moving. Duh, right? All of our experience tells us that as well. Or of uniform speed in a straight line. Okay, so this is the second choice, right? So he says every object can stay not moving, stay in a state of rest, or if it's moving, it's going to continue moving at a uniform speed. Uniform is another way to say constant or unchanging speed in a straight line. Unless acted upon by a non-zero net force, which is really what we talked about in chapter 2, right? We said that for an object to be moving, there has to be some sort of net force on it that's causing it to move. Newton's first law is saying the same thing. It's just saying it's a non-zero net force. So we don't have forces that are balancing each other out like we do in constant uniform straight line motion. It's saying it's every object's going to continue in this state of rest. Okay, so Newton's first law states that every object continues in a state of rest or stays at rest or stays moving at a constant speed in a straight line unless there is some force acting upon it. So first we'll talk about objects at rest. So we know that things or items or objects tend to keep doing what they're already doing. Right, so that's kind of summarizing in kind of simple terms what we talked about here. Right, this is saying if an object is not moving, it's going to stay not moving. If an object is moving at constant speed in a straight line, it's going to keep moving at constant speed in a straight line. Okay? So, objects in a state of rest or not moving tend to remain at rest. Only a force will change that state. So again, we're familiar with this, right? We don't expect to see some object start moving all on its own, right? We know that if an object starts moving, there has to be some sort of force present, some sort of push or pull that's causing that object to start moving. So if we look at our page 33 think question, it says a force of gravity between the sun and its planets holds A force of gravity between the sun and its planets holds the planets in orbit around the sun. If that force of gravity suddenly disappeared, in what kind of path would the planets move? Right? Gravity is that force that's holding it there and keeping it from moving the way that Newton has described. So if it's going to move in a uniform or constant speed in a straight line path. So it would move in a straight line path at constant speed. So what about objects in motion? Okay. Newton's law says that in the absence of forces, so if basically what we're saying is if there are no forces present, a moving object tends to move in a straight line indefinitely, which basically means forever. Okay, so that means kind of without stopping. Now, this is one that maybe is a little bit harder to believe because this is not our experience here on Earth, right? We don't see a moving object move forever without stopping. However, why is that? That's because we have friction everywhere on Earth. So Newton's law of motion is saying if there wasn't friction, once I get an object moving at a constant speed in a straight line path, it would do so forever. Out in outer space, that's what would happen. Probably the best sort of everyday example of this is a hockey puck on an air hockey table, because the air really significantly reduces the friction. And so it's almost like that hockey puck moves friction free, right? Eventually that hockey puck also will stop on that air hockey table, but it definitely keeps moving for a much longer period of time than most other objects we're familiar with. So, two little last questions for you to think about. What would be the motion of a ball tossed in empty space? So we're kind of just talking about like we are in outer space, okay, and we throw a ball. So away from gravity and other forces. So according to Newton's law, first law, how would we describe the motion of this ball? Hopefully you said a straight line path at constant speed. So a second thing to think about, consider a rock swinging in a circle at the end of a string. What is the path of the rock when the string breaks? Now you can kind of replicate this, but not using a rock. You can take, if you have like a lanyard, and you put your car keys or some sort of key on that lanyard, you can kind of replicate this and kind of see what happens. I will caution you, be careful when you let go. Sometimes it's a little hard to predict where your keys are going to go and what direction they're going to go. But you can actually kind of demonstrate this. This might be a good thing to go outside and try. Okay? Again, according to Newton's law, right, the only force that's kind of keeping this rock swinging in a circle is that string. So what's going to happen when I cut that string? Well, we know that rock's going to keep moving, but how is it going to keep moving? It should move in a straight line. Okay? At constant speed. Now, we know in reality it doesn't, right? Because what's going to act on it? Gravity. So until gravity starts to pull it down. And decrease the speed. But right after you release your keys, when you're swinging them in a circle on your lanyard, you'll see that straight line path. So that is the end of our Chapter 3, Sections 1 through 4 notes. Have a great day. I'll talk to you tomorrow.